This is dealing with the transition state diagrams. Now, transition state diagrams are a way to illustrate the changing energy, change in internal energy of the system as it goes from reactants to products. And when we talk about energy change in chemical reactions, for all reactions, two events must occur. One, a change in energy, in internal energy, or intrinsic energy, some people call it. And two, a change in the state of order. Now, these two considerations lead to in the first case, the first law of thermodynamics, and it is the study of internal energy changes in physical and chemical process. And the second one is the second law of thermodynamics, in which we consider the tendency of a process to be spontaneous or not spontaneous as it moves to a more disordered or more ordered state of existence. And we will be limiting our comments right now to the change in internal energy. Now, when we talk about changes in internal energy, we reference terminology such as endothermic or exothermic as it applies to the chemical process. So changes in internal energy can be either exothermic, which is a loss of energy from the system, or endothermic, which is a gain of intrinsic internal energy by the system. And these are illustrated in terms of an energy using simple energy graphs, a line representing energy change. If we consider the exothermic type reactions, the initial internal energy of the reactants might be represented as being in this position, whereas after reaction the products are represented as a final energy level right here. And so the transition is to give off energy from the system in general. And so that represents the heat of reaction, and this loss of energy is represented as a minus or change in energy. On the other hand, if we're talking about the system gaining energy, we find that we have an increase in internal energy, and energy is gained by the system and represents a higher internal energy when the reaction is completed. The process of going from reactants to products in either case must go through, according to the collision theory, an activation energy. So using this idea of energy diagrams, we can also show the process going through an activation energy. Now, the potential energy diagram for an exothermic reaction would look like this, in that the reaction or reactants, I'm going to say reactants R and products P, start at this position, so that'd be the energy of the reactants or initial internal energy, and this point where the products are is after the reaction is complete, positional energy after reaction. Now, there's some terminology you need to be familiar with as you go through this that represents different parts of this diagram. So we're going to split this in right down the middle here. Like this, and look at the energy change from here to here. This point right here is the activation complex, or the activation point, and the activation energy is going from ER to EA, and from ER to EA is the gain in energy needed to reach the activation complex. So we'll put a little diagram. Let me see if I can get a color. Okay, now in this diagram we want to identify the blue arrows as energy changes, and what we call the blue arrow here between the reactants and the activation energy is the activation energy for the forward reaction, delta E, I will call that F, and we'll list that delta EF right there is the activation energy for forward reaction. So you have to put that much energy into the process or the system in order to drive it to products. On the other side, this is the activation energy from the product side to the activation point for the reverse reaction. So this would be delta E reverse, maybe RV. So delta E reverse is activation for reverse reaction right there. Now, there's one more that you need to be aware of. The difference between the energy, internal energy of the reactants and the internal energy of the products is the heat of reaction, or enthalpy, E-N-T-H-A-L-P-Y, or heat of reaction. So this is delta E of the reaction for right now. And we'll just simply call that a heat of reaction. So delta E Rx is the heat of reaction, which is the energy of the products minus the energy total of the reactants. Products against the reactants. This is the change in energy. And as we look at the exothermic reaction and we notice that this position is below the reactant position, the heat of reaction for exothermic reactions is always less than 0 or negative. Right there. So that's how you can identify, one way to identify endothermic and exothermic reactions. Now, the potential energy diagram for the endothermic reaction is given by this illustration. Here is the reactants. Notice the products level is above the reactants. In other words, we have a higher energy now for the system after we have completed the reaction. So from energy of reactants to generate enough energy to react, going to the activation point, this would be the delta E for the forward reaction. Should have done that in blue. I'll change that. Let's do that. Delta E for the forward reaction. Now the product's starting here, and if you wish to go in the reverse direction, this would be the delta E for the reverse reaction. So the differential between the products and the reactants is the heat of reaction. Delta E for the reaction, in this case, will be greater than 0 or positive for the system. And so we have delta E for the forward reaction and then we have delta E for the reverse reaction. And the heat of reaction for the endothermic is delta E for reaction. And we will in the future, when we get there, appropriate time, be talking about energy in terms of an enthalpy or heat of reaction. Right now we'll just keep it as an E function and call it heat of reaction. And this is always greater than 0 for endothermic reactions. Okay? Now, we need to show you a couple problems, one for the exothermic and one for the endothermic, so you have a reference when exam time. Okay, here is a typical problem dealing with the exothermic type reactions, where you are asked to sketch the potential energy diagram, a term for the diagram, potential energy diagram, for this reaction. And the forward reaction has about 10 kilojoules. The overall reaction change in internal energy is 200 kilojoules. What's the activation energy for the reverse reaction? Okay, you want to begin by drawing out a reaction like this, and then noting the activation point, the forward reaction and the reverse reaction. Begin by establishing a note to the potential energy line here, and then drawing over, say, to here. Okay, that's the energy of the product. So since the energy of the product is below that of the reactants, you can expect it to come out negative or exothermic. Okay, now we are given the activation energy of the forward reaction here is equal to 10 kilojoules right here, and the heat of reaction, go ahead and extend that a little bit, show where it goes, is a 200 kilojoules between here and here. Is exothermic, so it would be below the starting point, that is your reactants. And the question is, what is the activation energy of the reverse reaction? Well, geometrically, the length of the forward energy line plus the length of the reaction energy line is equal to the length of the reverse activation energy. So delta EA forward plus delta E of the reaction is equal to delta EA for the reverse reaction. Even though it does come out negative, which it is supposed to, it has to use that magnitude, 200 kilojoules, in order to add to the forward activation energy to get the appropriate reverse activation energy. So the forward is 10 kilojoules plus 200 kilojoules, and so that equals 210 kilojoules for the reverse reaction activation energy. Okay, now we want to look at the same kind of problem, but dealing with the endothermic potential energy. And here you need to sketch the potential energy diagram for this reaction given the data as listed. So if it's an endothermic reaction, you want to draw it with a trend where the products come out above the reactants. So the E products up here against the E reactants here, such that when you take the difference between the two energy contents, you have a number greater than 0. And so this is a characteristic of the endothermic reaction. Okay, so the forward reaction is 257 kilojoules. So we have 257 kilojoules for the forward reaction. And the heat of reaction is endothermic here, so it's going to be equal to 167 kilojoules. Now, from the geometric graphics of the diagram, the activation energy for the reverse reaction and the heat of reaction equals the activation energy for the forward reaction. So when you add these two, equals that. So we have delta E, say forward, is equal to delta E reverse plus delta E of the reaction. And since they're asking for delta E of reverse right here, then we'll subtract both sides delta E reaction. So delta E reverse is equal to delta E forward minus the delta E of the reaction, and so we have 257 minus 167 kilojoules for the reverse reaction, and it is endothermic. And that one is a plus 90 kilojoules. Okay, so that completes the study of our introductions to the kinetics, chemical kinetics, and so forth. So we'll be beginning equilibrium after we do our lab next time, and so you might want to look at the videos on that